When we have fluid flow problems, we have two main types of problem for this course. One is that we don't have any kind of friction to worry about and we don't have a pump. The flow just happens because of some pressure difference, whether that's due to a height difference, actual pressure difference, gravity, what have you. There's no pump that's actually helping things out. The second type of fluid flow problem that we have is with a pump. And when we have a pump, we take all energy into account, which means we can't neglect friction. So that second type of problem is the second fluid flow video. In this video, we're going to focus on the Bernoulli equation, in which there is no pump and we're ignoring friction. And these assumptions are generally pretty good for thin fluids that are flowing under their own weight in a relatively frictionless line. So something like a hose, a plastic hose, where there's not a lot of friction buildup. Let's take a look at what those problems look like. Here's a sample problem. We have water draining from a pool. Water is draining through a hose, and if we look at this problem, we don't have a mention of a pump. We don't have any mention of anything actually attached to the hose, so no elbows or valves or anything in the hose. Water's pretty thin, so our Bernoulli assumption should be okay for this problem. We're given the rate the water is draining from the pool, we're given the relative height of the beginning and end of the hose, and we want to figure out what's the diameter of the hose that's used to drain this pool. Okay, given that we're doing the Bernoulli equation, it's tempting to say, okay, well, we know it's Bernoulli, let's jump right in and do it. Well, first we got to draw that diagram because this really helps, especially setting points 1 and 2 in the diagram. Knowing where your first and second point are is critical to being able to solve this problem correctly, because you have to be able to know the information at points 1 and 2. So if you put them in the wrong place, you can start making some very incorrect assumptions. And when that happens, your answer is going to be off at best. So let's start with our diagram. So here's our pool. Just draw a little cylinder. There's the hose coming out of the pool. The height difference between the start and end of the hose, we know that it's 0.75 meters. All right, now we need to set points 1 and 2. We are given information about the water level in the pool. And we're also given information about what happens at the exit of the hose. So it's a really good idea to set points 1 and 2 at those places because that's where we have information. We're going to set point 1 at the water level of the pool, so right there, and we will set point 2 right here at the end of the hose. Okay, now that we know what points 1 and 2 are, let's get that Bernoulli equation written out. The Bernoulli equation relates pressure at points 1 and 2, velocity at points 1 and 2, and height at points 1 and 2. And when we get finished, the Bernoulli equation without any terms canceled out looks like this. Okay, now we need to figure out what terms we can cancel. Let's take a look at our pressure terms first. Point 1 is at the surface of the pool. Point 2 is at the end of the hose. At the end of the hose, we're going to assume that's atmospheric pressure because there's nothing blocking that end of the hose, otherwise it would have been in the problem statement. At the top of the pool where the water level is, we see that there's no cover on the pool. That means there's nothing affecting the pressure at the top of the pool. It's open to the atmosphere. So it too is at atmospheric pressure. So what we can do here is say, well, P1 and P2 are equal to each other. Therefore, they're going to cancel out. So we'll cancel P2 with P1. All right, let's look at our velocities next. We are given that the level in the pool drops very slowly. That means that the velocity at point 1 is really slow. And if it's really slow to an engineer, we say it's 0, don't worry about it. So that first velocity term, because U1 is 0, this term goes away. But what about at point 2? Well, we know at point 2 that there has to be some kind of velocity because water is flowing out of the end of the hose. We don't know what that is, but it has to be something. So we can't get rid of that term. And in terms of our height, we can't get rid of any of our heights because we don't know what the height at point 1 and point 2 is. We know their difference, but we don't know the height at point 1 or point 2. But we can take care of that if we take all our crossed out terms out of our equation and rearrange so that we have the velocity term on one side and the heights on the other. So let's do that. Okay, let's collect terms. On the left-hand side, we have rho and g that are multiplied by z1 and z2, so we can squash those terms together. And when we do that, all right, we're almost done crossing out terms. We have one more thing to cross out. Notice how rho is on both sides. So if I divide through by rho, that goes away completely. And when you do that, this is what you get. Not too bad. Okay, we are given z1 minus z2. That's the 0.75 in the problem. We know what g is. It's the gravitational constant, 9.81 meters per second squared. We don't know what u2 is, but that's okay because it's the only unknown in our equation. So let's plug all our numbers in and see what we get for u2. There you have it. U2 equals about 2.71 meters per second. But we're not asked for U2. We are asked for the diameter of the hose used to drain the pool. So to get that information, we are given the volumetric flow rate. We know that's 1,500 liters per minute. But if you divide 1,500 liters by 1,000, you get 1.5 meters cubed per minute. And if you divide that by 60, then you get 0.025 cubic meters per second. So after you do that, volumetric flow rate is related to velocity through cross-sectional area. Volumetric flow rate is equal to velocity of what's in your pipe times the cross-sectional area of your pipe. And that means that the velocity is equal to the volumetric flow rate divided by the cross-sectional area. And the cross-sectional area of a pipe is pi times the diameter squared divided by 4. So that's how velocity and diameter are related. So let's get diameter by itself. What I did there was just move everything that was below the volumetric flow rate up to the other side to temporarily be on the same side with our velocity u. This is how I'm going to start getting diameter d by itself. Okay, what I did there was just divide by pi, divide by velocity, and multiply by 4 to get d squared by itself. And now to get that squared off of the d, we'll just take the square root of both sides. And there we go. That's the formula for diameter. Now when we plug in our values for volumetric flow rate and for velocity, we'll find what the diameter is. So let's do that. And there you have it. Our diameter is about 0.1 meter or 10 centimeters. So it's a pretty big hose, but keep in mind that we are losing about 1,500 liters per minute through this hose, so it needs to be pretty big to carry that particular flow rate. There you have it. That's our first fluid flow problem. This is the Bernoulli equation. If you're curious about what the full fluid flow balance looks like, including pumps and fittings and friction in the line, then I encourage you to check out the Solving Fluid Flow Problems 2 video, which deals with that full energy balance. But in the meantime, play around with the Bernoulli equation, see how the terms cancel out, try different scenarios with different pressures, different velocities. This is just one example of how the Bernoulli equation can be used.